Remember originally how many gates we required? One gate here with 3 inputs, another gate here 3 inputs, another gate here 3 inputs, AND gate with 3 inputs, similarly AND gate with 3 inputs, and then you needed 1, 2, 3 OR gates, right? That gave rise to your final Boolean function. Now look at this. This is exactly same as this. Now this required 2 input AND gate, 3 of them, and required 2 OR gates. So reduce the number of gates. Okay. So given a Boolean expression, by some using your brain, you can possibly reduce it to some simpler forms. But you cannot always do it when the expressions are too big and too complicated. So is there any logical way of doing this minimization? Okay, that is what is known as the Karnaugh maps. Okay. So let us keep this function and write the Karnaugh map of this. There are 3 variables and each variable can take on a 0 or 1. The possible combinations are 8 combinations in this case, and in this case there is D is defined for all possible values of A, B, C, right? In our truth table, all 8 possibilities are included in the truth table, and the resultant decision D is a Boolean function of A, B, C, which is given by this expression. How do I graphically represent this? I draw a BC, 2 variables. How many combinations can it take? 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. So because the 2 variables here, let us make it a 4 columns. And this column is, whereas this one is only 2 possibilities, A, so either 0 or a 1. This is 0 or 1. This BC will be 0, 0, 0, 1, 1, 0, 0. Here you have to use some care that you put 0, 0 here, 0, 1 here, and normally you would have put 1, 0 here, and then you would have put 1, 1 here, right? Don't do that. Try to do 1, 1 here and 1, 0 here. We'll just see in a few minutes see why I am doing it. There is no change. You still have the 4 possible combinations, only you shuffle them in some manner. What is the manner you have shuffled them? Keep this in mind. This is 0, 0. The next one is 0, 1. How many bit change is there in this? 1 bit change, right? And if you put 1, 0 here, like in normal way, the number of bit changes would have been 2. But in this way, what you have done here, the number of bit changes is equal to 1, and from here to here also the number of bit changes is equal to 1. So from one combination to next combination, you are making sure that the number of bit changes is only equal to 1. Such coding of Boolean variables such that the function has only 1 bit change, I mean, is what is this code is known as the gray code. I don't know, A or E? I thought it is E. There is a person by name Gray proposed this change of grading system from the normal binary grid to a version like this, where every time there is only one bit change. This became very important when you are doing the shaft encoding in rotating machines. So, every time you changes by an angle, only one bit changes, not two bits. So, because of this reason, this gray code has been invented, and this become very popular gray code. In other words, given this BC code 0010, you can convert it into gray code by a combinatorial logic. And one of the assignment problems I am giving you is how to convert a binary code into a gray code by using combinatorial logic. Very simple to do that. So, you can do that. You do that and put those values here. Now, in this table, what is C? What is your D? Look at your truth table. Easy to see the truth table for this. Truth table was 0, 0. Look up your notes. 0, 0, 0 correspond to 0. 0, 0 correspond to 0. The second one is 0, 0, 1. 0, 0, 1 correspond to 0. 0, 1, 0 corresponds to 0. 0, 1, 1, 0, 1, 1 corresponds to 1. 1, 0, 0 corresponds to 0. 1, 0, 1 corresponds to 1. 1, 1, 0 corresponds to 1, and 1, 1, 1, right. So, this is the truth table written in this format, which is the Karnaugh map. This map is called the Karnaugh map. Now, let us look at this. This is 1, this is 1, and when does it happen? It tells you these are both 1, when this is either 0 or 1, but this is only 1 and 1. So, A becomes irrelevant in this. So, this is only left, that is BC. So, I got my term BC. So, this is my term, which is BC. And we have agreed same term can be used any number of times. So, let us look at this. What does it mean? The term which is changing in these two, 1 and 0, is irrelevant, right? What is changing here? The first fellow, which is B, whereas A is 1, so it has to be, it corresponds to AC. Are you with me? And there is another combination here, 1, 1. If we look at this, this is coming from, what is the change, 1, 0? This C is a 1 and a 0, so it is irrelevant. So, what we are left with is A and B, that is this term. So, you look at neighbors which are 1s. In this case, the neighborhood is either a vertical line here or a horizontal line here. Take two of them which are neighbors, which are 1s, and look at the corresponding ones in which there will be one Boolean variable having both 0 and 1 values. So, that is an irrelevant variable. So, remaining is what is left. So, look up and exhaust all possibilities in this, and automatically the resulting expression is the minimum expression, provided you have done it carefully. Okay? And bell is over. So this is the minimization technique, simple minimization for 3 variables. If you have 4 variables, what do you do? Same idea. Here you take 2 variables, here you take 2 variables, but this arrangement of the 2 variable combination must be again a gray code variation, and then put your functional value corresponding to the Boolean variables, and then try to look for neighbors. Okay? So by this process you will be able to simplify the Boolean expression, which requires smaller number of gates compared to the original expression. And the output of this, if you do correctly, will always be a minimum realization. That's why it's called a minimal form. This form is called the minimal form. So the Karnaugh map, once upon a time, 1960s, used to be a very powerful tool to reduce the number of gates in a logic circuit when the gates were very expensive. So minimization was reducing the number of gates, the cost of the realization was reducing. But today I don't think it is much relevance to us. But the beauty of the mathematics is something which you should appreciate, because most of the time the chip contains so many more gates which you don't even use. We have become, as I mentioned last class, we are living in luxury. So the minimization is no more a very important issue. But I am told that if the machine is too big a machine, even then they will do the minimization to reduce the implementation cost of this, or to reduce this times which I mentioned for that purpose. But people went up to 4 variables. Now the question came up, how do I represent this in a pictorial form for if the number of variables become more than 4. It becomes very difficult. So people went into representing this mathematically and putting in a computer, and that is what led to called switching theory, how to minimize the number of variables are large number of variables.